Hi, everybody, and welcome back to Echo Live, coming to you from the Michigan Science Center. You'll notice that I am back in space today here on my virtual background because we are going to go ahead and we are going to talk about vacuum science part 2. So we've talked about our vacuum chamber that we have here once before on Echo Live, and we had so many great suggestions for things that you at home would like to see us put inside our vacuum chamber that we figured we had to bring it back. We had to try out some of those suggestions that you commented either through Facebook Messenger, through Zoom, through the chat, or during our program live. So I've collected some suggestions that you had sent to us, and we're actually going to test out your versions of this vacuum chamber experiment. So Echo Live is for you. So if after any of our programs or during our programs, if you have suggestions for experiments that you'd like us to try, please send them to us. We love trying things that you at home are curious about. And not everyone has a vacuum chamber like this in their house. And so this might be a little bit more difficult for people to recreate at home. But we're going to try out those suggestions that you sent in on our last vacuum science program. So a quick recap of the vacuum chamber. Today we are talking about vacuums, but if you remember back to last time in science, we're not really talking about the vacuums that we might have at home in order to clean our floors or vacuum out our cars. We're talking about vacuums in terms of places like space, like my background behind me here. So we're talking about vacuums, meaning that it is a space that is empty of matter, completely empty of all matter, including air. So we are actually using a vacuum. So I have a high-powered vacuum here that's going to help us to pull the air molecules out of our vacuum chamber. So they're attached by a hose. The pump is actually going to pull all of the air molecules out of our vacuum chamber. And then depending on the different type of object that we place inside the vacuum chamber, we'll see some different effects. So we'll start with something that we tried last time, but I did get a suggestion that maybe people wanted to see what would happen to just one little marshmallow peep inside the vacuum chamber. So last time we created a big pile of peeps. So this one can be kind of a recap, but also came from a suggestion. So we're going to take an up close look at what happens to this peep when we place it right here inside our vacuum chamber. So we'll set our one blue peep right there on the center of our vacuum chamber. This lid creates a nice tight seal with this rubber lining on the vacuum chamber. And then as soon as I find my remote, there it is. We'll zoom in on our vacuum here, and we're going to start removing the air. So the vacuum can be a little bit loud, but what we're looking for is what happens to our peep down there inside the chamber. So here we go. And our peep is starting to expand. If you think back to last time, this peep is full of millions of tiny air molecules or air pockets. And the vacuum is actually sucking those out from inside the peep. So even though we noticed that the peep grew at first, now it's actually starting to shrink back down again, right? So we're actually ripping those air molecules out of the peep, which is now causing it to be a little bit smaller. And then, of course, our favorite part, even more fun than putting things inside the vacuum chamber, is actually what happens when we let the air back in. So our peep did grow as it inflated those air pockets, and then it started to shrink again as we actually removed those air pockets from the peep, leaving it with less air than before. And now let's see what happens when we introduce the air back inside the vacuum chamber. Here it goes. Oh no! So we've got a tiny kind of deflated, almost crunchy little peep. So we've removed all those air pockets. Now there's not as much there to support the structure of the peep as there was at the beginning. And so we're left with just this one little squishy peep friend here. We had some other really great suggestions for things that we hadn't yet tried placing inside our vacuum chamber here. So one suggestion that came from Brian was we should try putting some ice cubes here inside the vacuum chamber. So I have a cup full of ice cubes here. We'll go ahead and place those in the vacuum chamber. We'll zoom back in. And then we'll start up our vacuum chamber one more time. Here we go. Now, not much is really happening to the ice, at least not much that's visible to our naked eye. Now, if we were to look very, very closely, there is a little bit of movement happening down inside the very bottom of the beaker. So there is some water that was created as these ice cubes started to melt before the program. And we can actually see that that water is starting to boil. What's invisible to our eyes is that some of this ice is actually starting to sublimate. Sublimate is the same phase change that happens to dry ice when it skips the liquid phase altogether and goes straight from a solid to a gas. So at this low pressure point, water is actually, or frozen water, ice cubes, is actually able to turn directly into a gas from its solid form. So we'll let our air back in and we'll go on to our next object here. So we did an experiment using water balloons in the last time, but just like this water balloon, there's nothing in it. It's just air that I've blown up just a little bit with my breath. But I also did fill one of the same balloons to approximately the same size. You'll notice that the water filled balloon is just a little bit smaller. And we're going to compare the two. So someone suggested, you know, they'd like to see what would happen if we put a water balloon inside the container that's actually full of water. So we'll just dump these in here. And we're just going to compare the effects between the two balloons. Again, we have the slightly larger balloon is full of air, and the slightly smaller balloon over here towards the front, that one is full of water. So let's go ahead and we'll turn on the vacuum pump and watch what happens to both. So we've seen some pretty amazing movement. So even though they both started off at approximately the same size, we've seen that the air-filled balloon has almost fully expanded to fill the container that it's in. We have to think about this in terms of those air molecules, right? We've removed the air from inside the chamber, but we've actually left all the matter inside the balloons intact. We're not removing any of the states of matter from inside the balloon. Since gases have a lot of energy, those molecules have lots of energy and they're floating around, right? They will try to fill the empty space around them. That's a property of a gas. So this air-filled balloon, right, expanded to fill the empty space that was left behind by the vacuum. But if you look closely at the water balloon, right, we really didn't see much change in its size. The water inside did start to bubble just a little bit as the water that was mixed in the balloon was removed from the water. But since water doesn't have that same property as gases do, since they don't expand to fill their container, and those water molecules have something that we call cohesion, they want to stick together, we didn't see much growth in the water balloon there. So if we had left it in here for a really long time, we would have removed all the water from all the air from the water. But we really won't see a change in size between the two balloons. So that's a really great demonstration of the differences in properties of our states of matter. So gases will expand to fill their container, whereas water is merely just held in place by their container. So I see some more great suggestions. Please keep sending those in. Type them in the comments. We can maybe even post another series of videos of what you want to see inside our vacuum chamber here. We'll do that next. I did get a good question about the PEEP, and the question was, does the PEEP still taste good? To me, the answer is no, but that's because I just don't like PEEPs to begin with. If anything, it might taste even better because you've actually just ripped out the air and left behind just a really densely packed sugary treat. So if you like PEEPs, you might like this deflated version of the PEEP even better than you like PEEPs normally. Great question. All right. I think we've popped our water balloon there. But we've got a few other things to try. So we'll make sure that we place this back down here. We've got some kind of nasty stuff coming off of our water balloon that's starting to leak. But we're going to move on and talk about something else that you suggested online, which is eggs. So someone suggested that we put cake batter in here. Didn't make any cake batter today, but I did see a suggestion for eggs, which is one of those ingredients that we find in cake batter. And so we'll place our 2 eggs right here in the vacuum chamber. Once we turn this on, I might need to grab some wipes for our container here. So we're gonna go ahead and we'll start removing the air from our vacuum chamber, and let's watch what happens to these eggs. We'll zoom in just a little more and turn it on. you may have noticed we didn't see quite a change in these eggs. So we're not seeing the eggs changing in size. That's because they're not really full of many gases. So again, just like if we think back to our balloon demonstration, these eggs are mostly full of a liquid. So they're not really expanding. They have that nice rigid shell. So even though eggs are, we consider them to be very breakable, they are quite strong, especially for their size. And so we're not actually seeing the eggs be shattered by the vacuum chamber here. We'll let the air back inside. I'm actually going to wipe my container really quickly. But I have something else we can try with these eggs. Now we said inside their container, they're kind of protected. They're almost sheltered from the force of the vacuum by their really, really strong structure. But let's see what happens if we were to crack these eggs and do the same experiment. So let's go ahead and we'll crack these eggs. Collect my shells back here. And let's watch what happens to these now, just the liquid or the inside of our egg next. So here we go, same experiment. I'll try to turn my glass here, try to find a clear spot and wipe this one more time. That balloon was kind of gross. All right, so here we go. Let's watch carefully what happens to these eggs. We have actually boiled these eggs. Now, just like if we think back to our first vacuum science, we are actually not increasing the temperature at all within this container. Actually, when we remove the air from inside, we actually decrease the temperature of the system. We have to think about the fact that when you take matter or molecules out of the system, like air, you're actually removing their kinetic energy as well. So there's not as many air molecules bouncing around, which actually lowers the boiling point of water and other substances like eggs. So we've actually boiled these eggs at a colder temperature than they started at. So we haven't cooked them at all. We've actually just, we've boiled them at a cold temperature. And so these eggs are still viable. We can still eat them later. I put them in a food safe container. And so I can actually save these and have them maybe for breakfast tomorrow. So we've boiled eggs. We've answered a few really great questions. And I have a couple more suggestions to work from. Someone did suggest what would happen to soda. And so who was it? Erica on our last video actually asked what would happen to carbonated soda. And I noticed that Charlie actually asked the same thing. What would happen if the water balloon was full of carbonated soda? So a liquid that has more gas molecules packed inside it. So I actually do have a small glass here of soda. We'll go ahead and set that down in our vacuum chamber. And then we're going to remove the air. So different than water, right? This soda has lots of gas molecules packed inside it or suspended in it. Those gas molecules are carbon dioxide. It's the gas that we exhale all the time constantly here on Earth. So even though we might not be able to see it all the time, if you've ever drank soda, you can actually feel those air bubbles inside. That's a big reason why people actually enjoy drinking soda. So let's go ahead and try this experiment next. So our liquid, right, is boiling just like our water would have, maybe even more violently than we saw with the water because this liquid has so many more gas molecules inside. Now you'll notice it starts to taper off, right? So we actually sucked out all of those carbon dioxide molecules, and now we're really just boiling that liquid. So at first we saw a big pile of foamy bubbles, just like if you were to shake up a bottle of pop and then release the pressure, right? We actually release those air molecules that used to be trapped inside. But now, if we let the air back in, we've actually removed those carbon dioxide bubbles. We've boiled it a little bit. And so if you actually taste our soda that we tried here, it's now really gross and really flat because we've actually removed those carbon dioxide molecules that make pop taste so good. So no more carbon dioxide, we've lost the carbonation. If I were to put this in a container and shake it up, there'd be nothing left to make it fizz. Now I have a couple more demonstrations to try. Another thing that was suggested in our last Echo Live program was, what about some bubble wrap? So you guys were thinking of really great suggestions of things that we know have air trapped inside them. So I've got some bubble wrap here. We'll go ahead and put it inside our vacuum container, make sure that we're not trapping it anywhere. Might have to pick it up. There we go. All right, so we've got some bubble wrap down there inside, and I'm sure you can probably guess what's going to happen to those air bubbles, the bubbles that make it bubble wrap, when we turn on the vacuum. So you go ahead and tell me what's going to happen to these bubbles once we turn on our vacuum and remove those air molecules from inside. All right, here we go. So our air bubbles are starting to swell. They're starting to swell. And just like all of our other experiments, they're starting to swell to a point where then we remove the air from inside and they're actually starting to pop. But this might be kind of disappointing if you're watching from at home. You might be a little disappointed because what is normally so satisfying about bubble wrap is that popping noise, right? We know that when we pop the bubble wrap using pressure, right, when you release that air, it makes that really nice popping noise, which makes it kind of fun to play with. But the cool thing about a vacuum is that sound actually cannot travel in a vacuum. Sound is what we call a compression wave, meaning it actually pushes together molecules in order to travel to the person that's hearing it. If you don't have any molecules to compress together to travel in a compression wave, you actually don't have sound. And so there's no sound taking place. We actually can't hear the popping. And so even though I can see that a lot of these bubbles have popped, you actually can't hear it, which kind of defeats the purpose. So we have another demonstration to show that. So using a different vacuum container, we've actually hooked up inside this container a bell that's powered by this vacuum. So before we do the vacuum experiment, I'm going to go ahead and we're going to turn on the bell so you can actually hear it ringing inside this container. Now keep in mind there's still air in here. We haven't created a vacuum just yet. And so we're actually going to turn on the bell and make sure that we hear a sound. All right, so we know that there is sound traveling right now because there's air molecules for that vibration to travel through. But if you don't have sound, or if you don't have a medium, if you don't have air, you also can't have vibrations. And so we'll actually lose that sound as we pump the air out of this container. So we'll go ahead and hook up our vacuum here. We'll turn on our vacuum and we'll see if we still hear a sound inside. Now the vacuum is pretty loud, but even if I now turn off the vacuum, our battery is still hooked up. That bell is still still moving. We're still trying to create a sound. If we get a little bit closer of a look at it, you might even be able to tell that our bell is still working. We've still got some movement going on. The hammer is still striking the metal surface, but we don't hear the ringing noise because there's no medium for that sound to travel through. Of course, if we let the air back in, we continue to have that noise, right? That sound. So this is a great time to pause for any questions before we get to our last couple demos here. So if you do have any questions, go ahead and type them in the chat for us. As always, this is a great time for us to take a moment to thank the sponsors of the Michigan Science Center. So we are very thankful to our donors like the DT Energy Foundation, to our other donors, and to members and people who are just watching these programs on Facebook Live or through Zoom that are donating to the Science Center so that we can still continue to provide these programs to you for free every day at 2:30 p.m. Eastern. So again, big thank you to them. Let's check and see if we have any questions. I know we've got a couple questions in our Zoom chat. Does that vacuum suck all the air out of the jar? Yes. So there might be a small amount of exchange of matter still, just since it's not a perfect system. This is not a lab grade vacuum chamber, but it is an almost perfect vacuum. And so the vacuum really does pull out all of the air from inside the plastic jar, leaving us with a vacuum inside. All right, let's see if we have questions from our Facebook audience as well. Can we do, so we've got a lot of suggestions coming in from people of things they would like to see. So please keep sending that. I see a suggestion for an episode on rocket science. We can absolutely talk about rockets. We know how to launch a lot of rockets here at the Science Center that are not safe to try at home, but I also see a suggestion, can we do a lesson that are kid-friendly experiments? We've done one episode already of Try This at Home Science, and we can certainly do more. So we can teach you how to launch some more kid-friendly rockets, teach you some different experiments that you can try at home. And if you're looking for more at-home science experiments, please visit the Michigan Science Center's website. We'll type a link in the chat as well. And it is just our website /at-home-science. And we have a whole list of activities that you can try at home using kid-friendly materials, things that you might already have at your house. Can we try a flame? So I actually did bring that one. That's another experiment that I think we can try here. So I do have a small tea candle in a glass container. And so we'll try the flame next. And so we'll get to that one. I see a few people suggesting that, and that's a very good question. So if you've been present for our combustion episodes, maybe kaboomistry, or where we've talked a little bit about the fire triangle, right? You know that fire does need oxygen in order to burn. And so if we remove the oxygen from the container, right, you can probably guess what's going to happen to the flame, but we'll try that in just a moment here. How does electricity make sound? So electricity by itself doesn't normally create a lot of sound, but it has some interesting effects on other objects. So electricity can power a motor, like we have here with this bell. So the electricity provides power to the motor, which then has mechanical energy, which turns that mechanical energy into vibrations. All of that is kinetic energy, right? And we just observe sound as evidence of that energy. What happens to electronics inside a vacuum container? That's another really great question. Not much really, because electricity is not a combustion reaction. So we can still have flow of electricity or movement of electrons inside a vacuum, which is really important because if you think of all of the equipment that we send to space that relies on electronics, right? We can actually have electricity powering things in the vacuum of space. And so that's a great question. We might be able to demonstrate that on a different episode of Echo Live. Maybe we can try putting some different electronic devices in here. But we do have this bell, which was powered by electricity. And we saw that it was still working inside the container. We just couldn't hear the sound, but we can try some other objects. If you have specific suggestions, send them to us in the chat. Let's see. We've got a few great suggestions. We could try, so we could try in a different episode. Someone suggested a pop can. I do have a pretty fun experiment using a pop can that we might be able to try. All right, so let's go ahead and I'll keep an eye on the chat. So if you do have other questions or suggestions, keep sending them there. But let's go ahead and we'll try our, we'll try this candle experiment here. Now, I think you might be able to see it a bit better if I maybe prop it up. And so I'm gonna prop up our candle, maybe just set it right here on top of our Pyrex dish. We'll drop it down inside our vacuum chamber. Zoom back in. And we're going to, we should probably light the candle, right? That's what we're looking for, is the evidence of what happens to fire, not necessarily the candle, right? So we'll go ahead, we'll just melt off a little bit of that protective wax. We've got our candle burning, right? Right now there still is air inside the container, but even before we turn the vacuum pump on, right, we can already see that the size of the flame is starting to diminish. We're running out of air already, right? Just there's that flame is using up the oxygen very, very quickly. But we'll see what happens if we kind of speed up that process. and remove the air with the vacuum pump. So here we go. We can see that the flame is still burning, although very, very small. Let's see what happens when we take away that oxygen from this combustion reaction. So very, very quickly, right, we've snuffed our candle out. We saw a small amount of smoke, maybe even a little bit of water vapor, but what we've done is we've completely removed the oxygen, therefore removing a piece of our fire triangle, and our combustion reaction has stopped. And so our candle has gone. Great suggestions, you guys. Now I only have one very last experiment to show off because I figured it would be fun to end with something that's a little bit fun and maybe a little bit messy. So we'll do our very last vacuum chamber experiment here. And we're just going to use some dish soap. So this was another suggestion we found in the comments of what might happen to soapy water or dish soap inside this vacuum chamber. So we'll go ahead and we'll try this, our very last vacuum science experiment. Here we go. We've got our container all hooked up. Let's take a closer look, and here goes the vacuum. So right now, right, we're waiting for that water to boil. We're waiting for the air to start being removed from the liquid. And we've created a giant pile of soapy bubbles. And I'm only letting it go on this long because my vacuum chamber was a little bit gross from our water balloon. And so now it'll be nice and clean when I go ahead and rinse it off later today. So we did see that that water started to boil. If you've ever seen our elephant toothpaste reaction, right, we rely on that dish soap to kind of trap that air inside. We get to see it in a more visible way. So I have a suggestion too for someone who'd like to know if we could demonstrate how a steam engine works. And that is a great suggestion. So thinking about these vacuum chambers and thinking about this movement of air molecules, right? You know that as we turn liquids into gases, we've talked about that they expand. We saw that with our air-filled balloon, right? That gases expand, that they can actually use that to turn it into power. And so we can actually demonstrate that. Possibly on a different episode here. Otherwise, we will definitely send out some resources to you about how you can actually use steam to drive engines. All right. One last question for the road on maybe just a quick recap on how this vacuum chamber works, right? This vacuum is a pump, so it is powered by electricity, but the electricity is not what's creating the vacuum. It's actually just powering the pump to remove the air from inside. This works just like a vacuum. This is just kind of a weird looking version of the same kind of vacuum you have at your house. And so we can actually create a vacuum, which then pulls the matter from inside this container through this one, and then it expels it into the air behind it. So please keep sending your suggestions for things you would like to see in the chat. We definitely are excited to keep bringing these programs to you every day or every weekday at 2:30 p.m. Eastern. If you enjoyed it, please share this video with your friends on Facebook. We'd love to see as many people as possible tuning in every weekday. And again, please send us your suggestions for experiments you would like us to try here on air, or if you'd like resources for materials or experiments that you can try at home. So thank you everyone so much for joining us for Echo Live today. We will see you again tomorrow right here on Zoom or on Facebook Live. Have a great rest of your day.